Okay, it seems that we are on record now. So okay, so I think we can start. So I'm Rami. Also in the class, Guy is here. Guy, can you switch on the video for a moment?
I don't have a camera at the
You don't have a
moment.
camera. So this is Guy, which does not have a
I
camera.
will have some later,
So
not
he is
today.
the TA. So Guy, you already know when are your TA sessions?
I didn't schedule it, but I mean it can be anytime basically.
Okay, so you will schedule it this week, and then you will ask them to send email to the students.
Okay. Yeah.
So yeah, so it's, I think it's 1 hour a week, Guy.
Yes.
So 1 hour a week. So now we have 2 hours the lecture, and at some other point, Guy will send you email about the TA sessions, which will be 1 hour a week, and there will be also homework, and Guy will also be responsible for grading the homework, and basically the homework will form your grade in the class, but the grade is just pass or fail. So hopefully pass, assuming that you participate and start doing the homework. And yeah, it's okay not to get all the problems right. And the aim that at the end of the course you will understand how to solve all the problems and all the material. We do not make any exams. And so we don't have fixed office hours, but you have your my phone call. So you basically can call me anytime between 10 a.m. and p.m. and 10 p.m. But usually I will, or either I will not answer or will answer, but will not be able to talk. So best chance to catch me is between 9 p.m. and 10 p.m. And then usually we'll be able to talk. But of course, you can fix any other meeting by email also. EMR.com or just call. We are on record. So what I said earlier, I will put all the records in Dropbox. I will try to do it each time the same day or the next day. If I don't do it, please remind me by email. And so there will be a link to the Dropbox from the calendar and from my website. So first I will put it on my calendar because it's much faster than the website. Hopefully I will also put them at some point on YouTube, but this may take time. Also, Guy, will you be able to arrange some, before Guy, everybody try to register via the FGS website, because basically this is the only way to communicate by emails, etc. So everybody just plan to come into the course. Never mind, you want if you're not sure that you will continue to the end, it's perfectly okay. You will not get penalty for not showing up to the exams, and there will be no exam anyhow. But if you will just stop coming to course and stop submitting exercise, you will not get penalty for that. Just register, so you will get all the messages that you need to get. Also, people that are not for Weizmann, they always can register. Just send an email to the FGS or via the FGS website. I'm not sure how, but it should not be hard. And you will all get. So you will be in the system and you will get emails, and it will be written that you was part of the course. And if you will submit exercises, you can get credit on it in other universities if the other universities accept it. Okay, yeah. So I think this is enough for administrative stuff. So let's start to talk about the first. So before talking about what is category theory, I want to give some motivation. So maybe the motivation going back to Felix Klein. And so at the, I think, end of the 19th century, Klein came up with this project of how to study geometry. And what he basically said, so at that time it was rather new, the fact that there is more than one geometry was rather new. And also for several millennia, there was Euclidean geometry, and then in the 19th century, people start to discuss hyperbolic geometry, spherical geometry, and many other geometries. And what Klein says that basically each geometry has its group of symmetries, and we can study the geometry via studying this group. So if we talk about Euclidean geometry, we have Euclidean transformation, so rotation and shift. If we have spherical, so rotation of the sphere. And projective geometry, projective transformation, affine geometry will allow affine transformation, not only rotation, but also linear transformation. What else? Of course, hyperbolic geometry, etc. So this was the idea: study geometry using the group. And if you're going half a century back to the beginning of the 19th century, you see that this basically the point of birth of group theory was also from studying symmetries, but not of geometry, but of fields of polynomials. Yeah, so Galois and probably Ruffini and Abel before him studied symmetries of equations. Yeah, so Galois did much more systematically, and Galois theory via groups. So basically, the motivation of existing of motivation for groups is studying symmetries of some other objects. And closer to the end of the 19th century, it became much more popular, in particular because of this idea of Klein of study geometry via groups. Okay, this was all very nice. And so as you see, it's not necessarily for geometry. You can study symmetries of everything. So this is a great motivation for studying groups. The problem is that it doesn't really work. So it works sometimes. But now imagine you have your nice sphere that have very nice group of symmetries, and you can study spherical geometry via groups of symmetries of spheres. Then you take a hammer, and you imagine your sphere is for metal, and you hit your sphere with a hammer. And then the sphere stops to be very nice and becomes something like that. And it doesn't have any symmetries anymore. So you cannot study anything with a group of symmetries of such things because it's a trivial group. So no difference between this thing and say one point. And so it doesn't work. And if you think about it, so you might think about two reasons why it doesn't work. So one reason is, okay, maybe the main reason is because you're fixing one geometric object. So of course, if you have this sphere and you have the, say, three-dimensional space, so this sphere can be put in many different ways into the three-dimensional space. It just cannot be put inside itself in many different ways. So you can allow more objects, more geometric objects, or more objects to put here. And another thing that you can allow, so what is symmetry? Symmetry is a mapping between the object to itself, like you have to put any point to some new point that preserve all the structure. So preserving the structure is kind of essential because otherwise you're not studying the structure. But also you want it to be invertible. So it's group of symmetry. Everything that you do to one direction, you want to be able to reverse. And this is very nice, but you may let it go. Of course, if you're talking about maps between two different objects, then if they're actually different, they're not isomorphic, you're not expecting them to be invertible. Yes, so you can put this curved ball into the space, but not in an invertible way. You cannot put the space into the ball. So you let go the invertibility thing, and you let go the idea that you have to work with symmetries of one specific object. And this basically what gives you the notion of category. And so in a sense, the reasons to study categories are basically the same reasons to study groups. They're just even more useful because they can be used wider. So let me start now with a formal definition of a category. So definition. So to have a category, you need to have two things. You have to have a collection of objects. If I want to make my life easier, I will say a set of objects. But in practice, we often want to talk not on larger collections of objects which does not form a set. For example, all sets that you know that is too large to be set. But it's not a big deal. So you should somehow, yeah, in this course we will somehow ignore it. There are some techniques. So some theorems that we will prove only for cases when we're talking about sets of objects, so that will work only for categories that are called small categories, where the collection of all objects is actually a set. And but anyhow, it will not be a big deal. It can apply them for larger cases. You just have to be careful. And for any two objects A and B, you want a set more A B. This is for any A B. Morphism between A and B. And again, when we intuitively think about it, we think about A and B as some structure, or maybe geometric structure, algebraic structure, some kind of object. And morphisms between them are actually transformation between those structures, between the underlying sets. They have to preserve some structure, etc. But this intuitively. But formally, when we define a category, we don't require it. It's like with group. So yes, when we think about group, we usually want it to be groups of symmetries of some object. But when we define groups, group is just set of elements, and each element is just a name. You don't think about it as transformation. You can think about it as transformation, but you don't have to. So here also, the morphisms between A and B are just elements in the set of morphisms. They don't have to be actual transformations. They often will be, but they don't have. And of course, as in a group, you have composition, you have product, or which coming from the fact that you can compose transformations. So in the category, you also have what happens here. You also have composition. So you can have a morphism between B and morphism between B and C. So to any pair of such morphism, you want to get a morphism between A and C. And this will be called composition. So, and you will write as usual, if you first perform F and then perform G, so you write them like this, D composed with F. Yes, so F, G. Yeah, this is the way we will use a single composition as we use it usually. The only thing is that we are composing, we're not actually composing maps here. It's just elements of the set. So set of morphism from A to B and set of morphism from B to C. So you want the composition, and of course, you want the identity map. So I said we do not ask the things as the morphisms to be invertible, but we still any object have the identity map which satisfies the usual axioms of identity. So we also want to have identity in more from, let's call it identity A, in more from A to A. So this is a structure that we need for category. So category is this collection, a pair, set of objects. For any two objects, set of morphism. For any three objects, a map, which is a map of sets. Yes, it's called.
Rami, excuse me. How do you define more of two functions?
So I don't define.
How pronounce what is the meaning behind it? Like
so this is a morphism.
Morphisms. Yeah, okay.
You think about it as a set of transformation between two objects. But this is just a set, and in order to define a category, you have to define the following data. Collection of objects for any two objects, set of morphisms. Here it's important that it's actually a set, more between A and B. For any three objects, a map of sets, a mapping of sets, which we will call composition. And for any object, an element which we'll call the identity morphism. And now they have to satisfy axioms. So until now, it was not axioms, it was just the data and structure. And now axiom. So what is the axiom? What are the axioms? So first axiom is associativity of composition. So basically it means that G composition F composition H equal to G composition F composition H. And here you have to have like three objects A, B, and C. And H is morphism. Sorry, 4 in D. H is morphism like this, F like this, and G like this. And then it makes sense to write all the compositions. So instead of writing, maybe I will write here, F is element of more AB, I can also write such diagram A, B, and F over. It will make my life easier. And again, I write as if F is actually a map, but I do not necessarily mean that. So F can be just element in a set that we call morph. And of course, about identity, G composition identity equal to G, and identity composition G also equal to G. A, B, and again, so here we first perform identity, so it has to be identity A. And here we first perform G, so identity has to be identity B. So if I'm not wrong, those are the only two axioms. So this is an abstract notion of category. So how are we going to use category in mathematics? So basically we can say two ways when category appears in mathematics. And the first way is in order to establish a language. So each time you have some theory, say set theory, group theory, topology, whatever, you almost each time have some underlying category. Because objects are just objects from your theory, say groups or sets, and morphisms are maps that preserve the structure. So if you have a set, so morphisms are just maps. Or if you have groups, then morphisms are just morphisms of groups. And so this is the basic way, the original way how we use categories. But we also sometimes want to use them like the mathematical structure by itself, in the same way as groups. So groups are very interesting by themselves, but of course, originally the first time we thought about groups is because groups are symmetries of some other objects. So in group, the situation here is a bit different. So in groups have a very rich internal structure. So you all studied in first degree in course in group theory, and you had lots of theorems about groups, even on the most basic level. And then of course you have some more advanced factors in groups. So in category theory, you don't see it immediately, and even until until now, most of the applications and the way we think about category theory is not because we want to study the internal structure of a category, but because we want to formalize some results in different branches of mathematics, to see relations between different branches of mathematics, or to see that the symmetries are somehow similar, or at least can be studied in a similar way. But with the time, we have more and more information about actually the internal structure of groups and of categories, and some actual non-trivial theorems about categories. So of course, naively, you can say that any non-trivial theorem about groups is also a theorem about category, because group is a special case of a category. How group is a special case of a category? You have category with one object, and so if you have category with one object, all the information that is left is just a morphism between this object in itself and the way to compose them. And because of the first axiom, the composition has to be commutative, and because of the second axiom, you have unity. So what you get is monoid. So categories with one object is the same as monoids. And groups are special case of monoids. So you can study, so anything that you can say about groups, it's also some statement about some specific categories. But you can ask, okay, what about categories which are not groups? Maybe you can, does they have internal structure? And the answer is, of course, yes, but it's less trivial and less useful maybe, and it's less fundamental than just groups. And I can see maybe two reasons. So when you pass between group to category, you have two generalizations. First generalization, that you allow things not to be invertible, and second, that you allow to have more than one object. So if you're allowing things to be not to be invertible, it already makes sense at the level of groups. You replace groups by monoid. And this is already an interesting question. So why we have all course in group theory and do not have course in monoid theory? Monoids are also interesting. There are many non-trivial examples of monoids. And it is true. There are many non-trivial examples of monoids, but there are not too many theorems about monoids. At least much less nice theory than you have in groups. Because just general monoids without any conditions, there is very little you can say. So you want to put some conditions. Of course, you can say that you put the conditions that all elements are invertible, and then you get groups. You can put other conditions and get some non-trivial theories, but it's harder than to do it for groups. Now, the second direction is replacing one object with many objects. And here, if you want just to go to the second direction without going to the direction of monoid, say I still want everything to be invertible, but I want to allow to have many objects, I get what is known to be groupoids. And groupoid does have a rich and interesting theory. But the problem is that on the first glance, this theory is just equivalent to group theory. So you get more things than just groups, but you don't really get more information. Or at least it looks like you just, every theorem you can formulate in groupoids, you can translate to the language of groups, so nothing new added. So of course, it's not really true. It's not true on some philosophical level, but it also becomes not true on the technical level. At the moment, you want to consider not only groups, but say topological groups with some additional structure. So groupoids with some additional structures becomes much more rich and interesting objects than just groups with additional structures. And this is a theory standing by itself. But it's more advanced than group theory, and of course, it's a good reason why we're not starting this study in the second year of first degree, but postponed it until now. Okay, so what we're going to have in the course. So the course will have kind of two halves, or maybe three parts. The first part will be about the general language of category theory. And here we will basically study category theory as a tool to describe fields in mathematics, theories in mathematics. So we will not we will not care too much about the internal structure of categories, but how we can use it in order to formulate statements in different fields in mathematics. And here the main thing will be lots of examples, because each time we'll have some theory of in mathematics, we will think about it as a category, and each notion in category theory that we will define, we will study how it behaves in all those examples. Then there will be probably some short chapter about groupoids. So groupoids have interesting internal structure. It's not that far from groups. So groupoids are categories where all the morphisms are invertible. And so if you have a map between A and B, so you have a map to the opposite direction from B to A, such as the compositions are identity. And so we will have a short chapter about groupoids, which have some internal structure and some nice applications. And then we'll go to some more advanced topics in category theory, relation with algebraic topology and other stuff. And I'm not sure how far we'll go into this third part, because in the end of the course, so we will take our time and we'll do whatever we will have time to do it, and whatever left will be left to next time. Okay, so this was about motivation and overview. Okay, any questions till now? No questions at all? Okay, so I want to say another administrative remark. So it might be a good idea that you will organize some meetings, Zoom meetings, outside the class and outside the TA. So if you need some Zoom room for that, I can open you Zoom room for that. Just any of you can send me an email and I will open when you want to meet, and it can be meeting for all of you or some parts. And so as we all know, this is not a usual semester, and we can try to use the technology to make it work as almost as good as usual semester. Okay. So examples.
Can I ask you a not formal question?
Yes, of course.
Is anybody? It's very hard to understand you in English, so I'll ask. Maybe is
so how many students we have here that does not speak Hebrew?
I do not speak Hebrew.
Yeah, I too cannot speak in Hebrew.
okay? So if there is somebody, okay.
Okay, so sorry. Yeah, I have a bad English. I'm really sorry about that. Yeah, I will. Feel free to correct me. By the way, I have also terrible grammar and spelling. I have dyslexia, so this is probably better to ignore. But if it becomes unignorable, so feel free to correct me. And if you didn't understand something that I said, just ask me to repeat it. I will try to do my best. Okay.
Can you put the microphone more closer to you? Maybe it will help, I think.
So it's on the camera and in front of
Oh,
the face.
okay.
So the other microphone does not work anymore. It will be a bit better. Is it better now?
Yes, because in the previous course, we heard you much better. So this is the reason.
So I need to buy another headset. Okay, I will ask one. Okay, next time I will bring from home and then we'll ask.
Can you maybe repeat the definition of a category?
Yes. So category is the following data. It's a collection or a set of collections that we will call objects. So the elements there will be called objects for any two objects. So for any two elements in ob, it's a set of morphism. We have a set of morphism, more from A to B. And for any three objects, we have a composition map like this. And for any object A, we have identity map. What?
What do we call morphisms?
Morphisms are elements of a set more AB.
Fair enough.
And for any object A, we will have a morphism from A to A that will be called identity A. So I say that morphisms are elements of a set, and identity is just one element of a set. But you should think about it as if there was actually transformations, actually maps. But they doesn't have to be like this. It's just the way you can think about it. The same way as in a group. So groups are just elements, and product of two elements of a group is just a third element, which is somehow predefined to you by the structure of the group. But secretly, you know that when you think about group, you almost always think about group of transformation of some object, and each element in the group is actual transformation, and product of two elements in group is composition of the transformation. You first perform one of them and then the other, like permutations. Yes. But it doesn't have to be that way. They can be just abstract objects which have abstract names.
So is it correct to say that the mole set is a ring or some basic common?
No, it's not a ring because each specific mole does not have any composition structure. But
no, not each specific one, the set of mole, because we can compose them and we have an identity.
Each specific set mole AB does not have any structure because we cannot compose two morphisms between A and B. But all of them together, they form something, some structure, which is called a category. It's not a ring, it's not a group, but it is a category. But yes, this is the way you can think about it. It's like another theory, but it's a little bit more complicated than you used to. Usually you have just one set with some maps on it, and here for any two objects, for any two AB, you have morphism between A and B. But we'll do examples and then maybe it will become clear. Sets. So this is probably the most basic category in the world, the category of sets. So objects will be just the collection of all sets. And all of you that study set theory, which I believe it's all of you, immediately will say it's a problem. Object is not a set. All the sets are not a set. Okay, so we'll deal with that problem somehow, but it doesn't have to be a set. And for any x and y, more x, y is just maps from x to y, all possible maps. This is a set, so no problem. And composition is just composition of maps, and identity is just identity map. So everything actually makes sense.
So by meaning that locally small, you mean that the morphism are set? What?
I never said the word locally small, but you're completely right. So for me, when I say category, I always will mean that more between x and y is set. So if you will open the literature, so in some places, they will not require that for a general category. They will just say we have class of objects and for any two object class of morphisms. And this will be called a category. And what this additional condition that more between x and y is a set, often called locally small. And small category means that also ob is a set. but all the categories that we will consider will be locally small, so we'll just call them categories. And in fact, we will behave as if they're all small. So basically, all the theorems that we will prove, all the constructions that we will make will be for small categories. But when we will want to use it in examples, the examples almost never will be small categories. And this is a bit frustrating. So we can either ignore it, or okay, in this class we will mainly ignore it. Now I'm not ignoring it. I will say something, but then in general we'll mainly ignore it. But the solution in literature is either just to ignore it, which is very common, or to say no, we just will talk about small categories, and we will not consider categories, large categories like categories of sets. Each time we want to consider large category, we'll have to replace it by some small one. So if we want to consider category of set, we will choose some huge set, I don't know, of cardinality 2 to the 2 to the aleph, or sometimes much more. There is some notion by Grothendieck of universe, of a huge set. And then we'll just work only with subsets of this huge set. And this will not be the category of all sets, but it will be good enough for any reasonable purpose. And there's another way just to learn set theory a bit better, and then to talk about classes and sets, all this model, all this approach of set theory when you have large things like classes and small things like sets, and you can consider the class of all sets, but you can't consider the class of all classes, and you can't consider the set of all sets, and then you can play this game. Okay, but in this course we will just use it. Well, almost always. Okay, so this is a basic example of category, the category of sets. Groups. Yes, so I believe any of you can guess what is the category of groups.
Homomorphism, like groups with homomorphism.
Exactly. Objects are groups, and morphism between two groups are group homomorphism, meaning respect the product and maps identity to identity and inverse to inverse. Now, abelian.
So, yeah, I have a question,
Mm-hmm.
Swami. Like, if you are taking the groups with homomorphism, is it unique? Like, can we take groups with isomorphism?
You
as
can.
the
It's a different category. So when you just say the category of groups, you always mean the morphisms will be just all homomorphisms. But you can do many different categories. The one thing that is really you can do, but it's really not a good idea, and you can talk about groups, and morphisms are just maps of sets, just maps, not more. So you can do it. It is a category, but it's a bad idea to do it. This category is, in fact, equivalent to the category of sets. We did not define the notion of equivalence, so I cannot say what exactly does it mean. But when we define it, you will see that it doesn't give you any new information. And so usually, if you have some structure, you have to preserve it. When you talk about morphisms, you have to preserve it. If you don't do it, it's the same as not to have this structure at all. So it's good to keep in mind. Abelian groups. So in general, if you have any category and you have some property, so you can pick some subset of its objects, then you get what's called full subcategory. All the objects become subset of the previous object, but all the morphisms are still the same. So morphism between two objects in the smaller category are just as before. And this is what happens when you pass between groups to abelian groups. More, or maybe I should not start with. Okay, I can do. Okay, I can do vector spaces. So here I have to fix some field f and consider vector spaces over f, and then morphisms will be linear transformation. And of course, I can do modules over an algebra. Okay, so let's talk about fields and algebras. So we can do rings. We can do commutative. rings. The same. And now we have something which is a bit surprising. Unital rings. So somebody can propose a definition of the category of unital rings. Somebody? It doesn't have to be correct. No one?
It's a tricky question.
You have a question?
Oh, I said it's a tricky question. You taught us in previous courses. Yes.
Ah. So if you know the answer, you can also say it. Okay, so the first guess would be, let's take rings, just a full subcategory of rings. So morphism of ring is morphism of rings. We want to know what it is. It's a map addition to addition and product to product. And now we want it to be a morphism of now we want the rings to be unital. Unital meaning just have unity, have one. But then you see that you don't get the answer you expect. That's because you see that there are examples of two rings with unity and map between them that does not map unity to unity. And this is not a good idea to consider it as a morphism of unital rings. So there is a notion of a morphism of unital rings, which means morphism of rings that maps unity to unity. So unital rings is a subcategory of the category of rings, but not a unital, but not a full subcategory. So the morphisms here are not all the morphisms here. Morphisms with unital rings have to satisfy additional conditions. Yeah, okay, and everything else you know in algebra you have fields. No. Okay, now we can go to maybe some analysis, some topology. We have topological spaces. What are morphisms between topological spaces and guesses?
Continuous function.
Exactly. Yeah, you maybe could have guessed that if the structure is open set, so it's something that maps open set to open set, but you all study topology, and in order to convey the intuition of topology, what does it mean? Something that preserves the topology, it's something that is continuous. So if it's continuous and invertible, so the inverse is also continuous, then you say it's homeomorphism, which means we consider that two objects are just the same. Okay. What do we have here more? So yeah, topological spaces. Metric spaces. So this is a tricky question. What is the category of metric spaces? It's a tricky question because I think it does not really have one answer. So you can consider metric spaces with isometries. It is a nice category. It's a bit too rigid to many purposes. So often people, when consider metric spaces, they consider all, let's say, Lifshitz maps. So you don't really have to preserve the metric, but you have to be not to change it too much. And of course, you can go to the other extreme and say you want to consider metric spaces, but the maps will be just continuous maps. So this is something that I said at the beginning is not a good idea, because if you have structure, you have somehow to preserve it. Otherwise, it's the same as if it does not exist. And in this case, it's not so bad idea, but it's really the same as if this matrix structure does not exist. So you can instead consider the category of all metrizable topological spaces. So topological spaces that have a metric. So the fact that one can find such structure is that the structure exists does give you information on topological space. But if you don't want your maps to preserve the structure, so it's the same as to say that you don't really fix the structure. So you can talk about the category of the metrizable space.
Maybe you can take maps that decrease the metric.
You not strictly decrease because you want identity, but yes, it is a category.
Yes.
Yeah, it's all. There are many possibilities. I think what is usually common is leaf sheet, but I'm not really sure.
Okay.
And it depends on the reference. Okay, now we can combine algebra and analysis. You can do topological vector spaces. So this is very nice category. The maps there are linear continuous maps, and basically functional analysis is about studying this category. You have two nice subcategories inside it. You have Banach spaces. And here there is some anomaly. Banach spaces is almost always considered as a full subcategory of topological vector spaces. So you could have said Banach spaces are just metric spaces, so why not talk about Banach spaces with isometries? But basically nobody doing it because Banach spaces have very little amount of isometry. So when people study Banach spaces, they study continuous maps. So this is a full subcategory. Continuous map between Banach spaces is the same like Lipschitz map, the same like bounded map. So this is all the same, but it's not the same as isometry. And now inside it you have Hilbert. And here there is a dilemma. When people study Hilbert spaces, they often study Hilbert spaces with isometries. It makes sense. Unlike general Banach spaces, Hilbert space have nice non-trivial isometry. So Banach spaces usually, if you just take a random Banach space, it will have no automorphisms that preserve the metric. But Hilbert spaces have a lot of them. So you can study Hilbert spaces, but then it will not be a full subcategory. And then there is this notion, not very popular today. I think that people just say what do they mean each time, but you still have this nice notion of Hilbertian space. So Hilbertian space is Hilbert space when you it's a Banach space or a topological vector space that have a Hilbert structure that defines the topology. So it means that when you consider morphism of Hilbertian space, you can just say that Hilbertian spaces are the same as Hilbert spaces, but morphisms are any bounded morphisms between Hilbert spaces. So you don't specify the specific Hilbert structure, you just care about the topology. So this is full subcategory, and this embedding and this embedding are not full subcategory embedding, or this embedding is just not full subcategory, and this is the opposite of being full subcategories. You take all the objects, but not all of the morphisms.
So Rami, so the Hilbert spaces category have that all that its isomorphism are invertible?
Not really invertible, but one-to-one.
Okay.
You can be isometry without being one-to-one, but you have to be one-to-one. So this is what more common. So I think again, each time you have to be a little bit careful when you read something. If somebody say something about the category of Hilbert spaces, you should verify whether it means isometries or continuous map, but more common that Hilbert spaces will be in isometries, and if people want to talk about general linear continuous map between Hilbert spaces, they would talk about the category of Hilbertian space. Yeah, so between Banach spaces and topological vector spaces, there are many interesting categories. So if you study them, it's good. So for shell spaces, locally convex spaces, and many others. You of course don't have to know it for the course, but it's nice to know in general. Yeah, in general, there will be lots of examples. And yes, in order to understand all of the examples, you need to know lots of mathematics. Yes. So if you don't know it, it's okay. But it's good to know at least 50%. So if you see that all the examples are new to you, so maybe it's better to take some background before or during the course. Okay.
Rami, I have a question.
Mhm.
So when you're saying that the Banach spaces are a subcategory of vector spaces and etc. about Hilbert spaces, so when you look at Hilbert spaces inside the Banach spaces, you have some extra structure that you somehow didn't have for an object
Yes,
as a Banach space.
I'm sorry. You need to be careful. I should have been more careful, and I can't be more careful at this point. So when I say Banach space is subcategory of topological spaces, there are two ways to do it. You can say that when we talk about Banach space, I don't mean that we have extra structure. I just want to know it exists. So I want topological vector space such that structure exists. So I can say it for Banach spaces. I can say it for Hilbertian spaces. I cannot say it for Hilbert spaces because I do need the extra structure. So yes, it is not an actual subcategory at this level. You can replace both of them with some equivalent categories, and then it will be a subcategory. But in this case, okay, I even did not define a functor. Yeah, so I can't say it at this point. And also can't say this. It's the same relation you have between metric spaces and topological spaces. You can start with metric space and make out with a topological space by forgetting something. You can think about it as an embedding, but in order to make it embedding, you need to change something. And okay, I will try to do it maybe even in the second hour. The second hour starting now, more or less. Okay, so let's take 10 minutes break. And meet here in 10 minutes. I will try to bring headset and maybe you will hear me better next time in 10 minutes. So see you. I'm leaving the room open so you can discuss. זה לא עובד. שומעים אותי עכשיו יותר טוב?
כן, כן, אפילו בהרבה.
וואו. זה חבל שלא ידעתי על זה קודם. Okay. So, yeah, we're exactly 10 minutes. So now I want to talk about different class of examples, which are not coming from modeling some mathematical theory. So one thing that I already said, a group. Not the category of groups, but a single group G can be considered as a category. So meaning object is just one point, E, and let's call it X, and morphisms between X and X is equal to G. And composition is just the product. Okay? Another example, a poset. Poset is partially ordered set. So you can consider it as a category. Yes, so if X, okay. More XY is empty, or is a singleton. No. If X more XY is a singleton if X less than or equal to Y and empty otherwise. Whatever. So the axioms of order set basically tell you that this is a category, the composition is the only thing you can do, like you have two singletons, so there's only one map, or only one possible way to define composition. And now special case of this.
Objects are the elements in the poset?
Yes. Yeah, so this example is not part of this paradigm that we had before, that we take some mathematical theory and study it as a category. It's the opposite thing. It's some combinatorial objects that have the same properties as category. So those things will have some intersection at some point, but as usual, yes, in group theory. So yes, there are groups that define to be symmetries of something, and there are groups which are just groups. But even groups that are just groups, they still often will become symmetries of something, and the other way around. So groups which are symmetries of something, they're also just groups. So special case of this poset thing is top X, so the topology on a set X. So what happens here? Objects will be all the subset U and X such that U is open. And we have an order relation on this, partial order, given by the inclusion. So this gives you a poset structure, which gives you a category structure on top X. Let's see, do I have some other examples of this type?
Okay. No, but I have
Subspaces of a vector space.
subspace of a vector space. Good, but yeah, it's also a poset or subset of a given set. Yes. So okay, never mind. Okay, I have now some little bit misleading examples. Categories. Yeah, probably it's more as a first question, or maybe not the first, but one of the questions that come to mind. Yes, if categories are nice language to talk about any mathematical theory, and we just said that it's also an interesting theory by itself. So if we want to study category theory, so we can study the category of all categories. So we kind of can, but it have two problems. Okay, first of all, we have to define what do we mean by that. So objects are categories. We have to define what are morphisms. And there is a notion which I will define soon of functors. And functor between two categories is basically a map that map object to object and morphism to morphisms and respect the structure. So you may think that you can be happy that you have the category of all categories. And there are two problems with it. So one problem that you probably immediately see is the size. Like the problem with set of all sets, category for category, you would go up too much up in size. So you have to play some games. So you can talk about category of small categories, which is good, but it's not a small category. Or you can fix some universe. You do categories of categories that can be embedded into this universe, and this category will probably not be able, you will not be able to embed in that universe, but it will be slightly larger. Not a big deal. But the other actual problem is that this does not reflect what you want to do when you study category theory. So you can study the category for categories, and then you can study notion of isomorphism between two categories. So we did not discuss the notion of isomorphism, so let me say it now. Just now, if you have two categories, if you have map between x and y, which is invertible, meaning that you have you have morphism between x and y, and morphism between y and x, such as this composition is equal to identity, and the other composition is equal to identity. So you will say that those two morphisms are inverse one of the others, and they're both isomorphisms, and the two objects x and y are isomorphic. And you remember that if two objects are isomorphic, it means that basically they are the same. You cannot like distinguish between them in the language of category of this category. So you can also talk about the notion of isomorphism between two categories. And it makes sense, but it's not good enough. So sometimes if two categories are isomorphic, it means that you cannot actually distinguish between them. But often when two categories are not isomorphic, you still want to consider them as the same. And the reason is that you basically want to consider objects which are isomorphic in the same category as the same. So you can, if you add some new objects, but they're isomorphic to the old one and no new morphisms was added, so you don't really want to feel that you change a category. And so it means that the notion of isomorphism of two categories is not enough. So I will discuss another notion of equivalence between two categories, which is weaker. And it basically means that you should not consider the category of all categories just as a category. It is a category, but it has some additional structure. Yeah, so another comment about this thing in terms of computer science. So what questions you are allowed to ask and what you're not allowed to ask when you're doing category theory, and when exactly. So of course so when you talk about morphisms between x and y, this is a set. And you're perfectly allowed to ask whether two elements in this set are the same element or not the same element. It's perfectly a reasonable question. But when you have two objects f, x and y, so they're both elements of orb. So we say that orb is not necessarily a set because of problems of size, but even if it is a set, it's still not very good idea to ask whether they are the same. Because, for example, take two vector spaces, V and W. So you all know what is direct sum of two vector spaces? Or even not vector spaces, you know what, forget about vector spaces, two sets, X and Y. You all know what is Cartesian product of two sets. And you know what is Y times X. Are these two sets the same? I see people giving correct answer, but without the microphone. Yes, so no, they're not the same. Those are order pair when the first element is in X and the second in Y. Those are order pair when the first element is in Y and the second is in X. It's not the same set. But for all practical purposes, you think about them as the same set. Those two sets are bijective. You have maps to both direction, very natural, nice maps. So, for example, when you want to talk about whether or not Cartesian product is commutative or associative, you will want to say yes, it is kind of commutative, kind of associative, but it's not commutative and associative as is, because just require commutativity or require associativity will require two sets to be the same. And the question whether two sets are the same is kind of meaningless. Another example, if you consider natural numbers, what are natural numbers? You don't really know. It depends on the textbooks that you're reading. Yeah, so Bubaki will probably say that natural number is a finite set whose elements are all the natural numbers which are smaller, strictly smaller than this number. So 0 will be the empty set, 1 will be the singleton of empty set, etc. But then after you read Bubaki further, you will see that they will define also integer numbers, which are pairs of natural numbers up to some equivalence, so equivalent classes of pairs of natural numbers. But then you always want to say that natural numbers are special case of integer numbers. And you see that you formally cannot really do it, because if you follow all the definitions, this set and this is not it's just not true, yes? But of course, it is true, or practically it is true. So you can redefine now the natural numbers to be integer numbers, non-negative integer numbers, or strictly positive integer numbers, depending on your taste. And of course, you have to do it again and again each time you introduce new numeric system until you get, say, to the complex numbers. So you have to have a model of the integer numbers to actually talk about it as a set. And before you have a model, you still know what is the integer numbers, but you're not talking about some concrete set. It's set up to some natural bijection or ring up to isomorphism or whatever it is, but you know what are the integer numbers, although you don't really have in mind some specific model. So talking about equality of two objects is not a good idea. And the way I like to make this analogy, to explain it, is via the analogy to computer science. So when you do object-oriented programming, you have private properties or private fields and public fields. So it's not that you cannot ask whether two elements are the same, two objects are the same. It is important when you define notion of category. So for example, you want to define what morphism can be composed. So I just said that composition is something like this. But you can say in general the composition can take any two morphism, and then you can ask whether they're composable or not. So in order to morphisms to be composed, the end of one morphism should be the beginning of the next morphism. The source of the target of one morphism should be the source of the next one. So they should be equal. They're not just isomorphic or something like this. They should be actually equal if you want to compose them. So when you define basic things in category theory, it's perfectly okay to ask whether two objects are the same. But once you getting out of category theory, or you want to use it, so don't use equality. It's not. It's a private property of the category. It's okay to when you define this category. It's not okay when you use it or when you use category theory. And this is why the notion of category of all categories, you can work with it, but it will lead you to wrong answers if you don't do it carefully. So it's like a private stuff of category theory. Once you leave category theory, you want to use it. So don't use this notion. There is notion of two categories. So category So the next level beyond categories, so something that can embrace category of all categories and use that. Don't use category if you want to discuss all categories. Unless you now defining something new, some new categorical notion. Okay. So let's see, what do we have here? Yeah, there are more examples here, but maybe not that. Okay, I can tell them. Yeah, more examples of the previous class. Yeah, manifolds. For this. If you know algebra, so you know, who knows what is a manifold? 1, 2. Okay, maybe I should. Okay, can you vote? Okay, we're like Tal did with this Zoom stuff.
Reaction.
A reaction, yes. Okay, only 2, but before several also said they know it. Okay, I see. Okay, probably. Oh, 1, 2. Okay, so more than half. Okay, you don't really have to know it to understand all the course, but it's good to read a little bit about it. So if you know algebraic geometry, so algebraic varieties, or other kinds of geometry, some other kinds of varieties, analytic varieties, etc. Now, if you have a group G, you can consider the category of G sets, sets with the action of G, and you have the category of representations of G, vector spaces with action of G. If you know what it is, if not, you can just ignore. So yes, lots of examples of this type. Now, type of morphisms. If you have morphism between X and Y, we discuss the notion of isomorphism. Isomorphism between X and Y is a morphism such that for any morphism to the other direction, it is the composition going to be identity. Now, if you remember in set theory or in group theory, you have, when you have isomorphism, usually before you have notion of monomorphism and epimorphism, or one-to-one and onto. So in general category, you also have those notions of one-to-one and onto. The problem is you have around 50 of them. So not really 50, but you can open NLab on the article of monomorphism. NLab, you know what it is, yes? It's kind of like Wikipedia, but only for math. And monomorphisms or epimorphisms. Epimorphism is even worse, and you will see many different notions of epimorphisms. Onto, surjection, epimorphism, weak epimorphism, strong epimorphism. So really lots of them. So if we don't want to discuss all of them together, okay, probably the most common one is what's usually called monomorphism. And it's a bit problematic to define it, because usually when we want to define what is monomorphism, we say that any two different elements will go to the same, will never go to the same element. But we have no elements. We are in general category. So morphisms are not actual maps, and the element and the objects are not actual sets. So we can't say it like this. And so the idea is like this, that, okay, definition. If phi from X to Y, phi from X to Y is monomorphism. If you have map, just a moment, if for any Z, the map, this is actually map of sets from where to where, let's see, more Zx to more Zy. And how this map work? For not for just for this is phi, yes. So we have a map from Z to X. You first perform it and then perform phi. Yeah, so map with composition with phi. Composition in the sense that you first perform your map from Z to X and then compose it with phi. And then you get map from Z to Y. If and only for any Z, the map Z is monomorphism. Yes, so this is one of the possible notions of when map is one-to-one. And now, instead of defining the notion of epimorphism, I will be lazy. And how I will be lazy? If we have category C, so I give another definition, I can define, or let C be a category, define C op, it's called the opposite category, in the following, this is ob and more AB. C op in the following way. I will write like this. The object of C op is the same object as C, just object of C. And morphisms in C op, if I write sub-index, which is a category, I mean morphism in that category between two objects A and B, are the same as morphisms in C between B and A. So I'm reversing all the errors. I define morphisms to be the morphisms in the old category, but to the opposite direction. Yes. Just a moment. I'll be back in a second. So somehow, from the point of view of abstract category theory, there's no any advantage of C op on C or the other way around. You see that the notion of category is completely indefinite for the fact that you change the direction of the arrows. But of course, if C is some reasonable, nice categories whose objects are actual sets with some structure and morphisms are actual morphisms, so usually C op will be something completely different and very often not something that you can think of it geometrically or so the morphisms are going to the other directions. They will have no sense of maps to the correct direction.
Can you maybe give an example of an opposite category?
Okay, I can give many boring examples. Just take vector spaces and talk about opposite category. This will be something else.
That's not a good example.
Because it's equivalent to the original one.
Finally, dimensional vector spaces, it's the same.
Okay, but I can do general vector spaces and it will be something weird. Finite dimensional vector space is not really the same. They're equivalent, but not canonically, yes? Guy?
No, it's not the same category. No, the category of finite dimensional vector spaces and its op are canonically equivalent.
Canonically or not canonically?
Canonically.
Okay, yes, canonically. But okay, but you can take any vector space, any dimension, and then you get not necessarily finite dimensional, and then you get something weird. Or sets, you get something very weird. So you can do it with any category, and usually we'll get something really weird. But sometimes you will get something nice. So, okay, so maybe one good example is what Guy said. If you have vector spaces, finite dimensional vector spaces, you will get something. I didn't say what is the equivalence of categories, but you will get something which is basically the category of finite dimensional vector spaces. but in very non-trivial way, or in some non-trivial way. But more interesting examples is the way to pass between geometry and algebra. So there are very nice construction. So if you have some geometric space, say compact topological space, so you can consider the collection of all functions from this space to R. This is a Banach space, but it also have a product. Let's do not for R to C. So it's a Banach space over C, it's have a product, and it's what's called C-star algebra. And if you have a C-star algebra, there is some way to reconstruct your original topological space. So it seems that you can make some dictionary, some equivalence between compact topological spaces and Banach and C-star algebras. They're very different, but somehow you can get from one of them the other. But it doesn't mean that the categories are equivalent. In fact, they're not equivalent because when you construct this dictionary, if you have a map between two topological spaces, X and Y, so you don't get a map between functions defined on X to functions defined on Y. You do get a map to the other direction. So this kind of equivalence that invert the errors. So in fact, it's equivalent between one category and the opposite one. So it's a rare example when you have two very different categories. Both of them, but somehow reasonable, they have sets. The objects are some underlying sets, and the morphisms are actual functions, and they become opposite one to the other. So the opposite category also have realization as a category, which is straight one, not opposite of another category. So you have other examples of this type in algebraic geometry. Yes, Tal? Tal?
You should also, yes, I have a technical issue. You should also mention the structure about the composition and the identity.
Okay, so yes, in the opposite category, the identity map is just the same, and composition basically just the same, because before, if you have maps like this, you could compose them. But now, the map from X to Y in the new category should be thought of as map from Y to X, and map from Y to Z should be thought of as map from Z to Y. So you still can compose them. So just you compose them in the opposite order. So everything works. Maybe another good example. Maybe this will be examples that explain maybe better the situation. You have a group. You can consider always the opposite group. You can consider a group whose elements are the same element, but the product law is the opposite. You multiply elements in the other way around. I don't know whether you study this construction in group theory or not, but probably a good reason why not to teach him in group theory is because it does not give anything new. So very simple exercise is to show that this opposite group is in fact isomorphic to the original group. If somebody wants to say the solution out loud now, he is welcome. Or hint or a solution. It means that nobody knows the solution. Guy, I assume you know the solution.
Yeah, but if nobody answers, then I will do it in the exercise.
Yeah, exactly.
In the tutorial.
And nobody else knows the solution? So if somebody knows, except of Guy, he is welcome to say.
You need to send each element to its inverse.
Exactly. But in categories which are not groups and not groupoids in general, it's not true. For groupoids, you always can do this trick. So, but from the point of view of category theory is completely symmetric to this passage between C and C opposite. And it means that each notion you make for C, you can make for C the opposite and get some dual notion. Sometimes it will be meaningful, sometimes it always will be meaningful, but sometimes it will be weird. So if you have the notion of monomorphism, you can describe the dual notion of monomorphism in the opposite category, which is called epimorphism, and it's okay. So this is the way it's defined. This is the standard way to define epimorphism. It's epimorphism in the opposite category. if you look at what this definition means, it will look a bit weird. And it indeed will be a bit weird. If you will talk about the category of sets, it will give the correct answer. So epimorphism is onto map of sets. But once you go to topological spaces or even to groups, no, groups is okay. No, groups, yeah, groups are okay probably. But many other examples, you will see that it's just not giving you your first guess. But this is still what's called epimorphism in general category. And this is why for epimorphisms there are more popular, more notions, but in fact, any version of notion of epimorphism, you can construct a version of notion of monomorphism. Just monomorphism, the first version is also the one that you actually want to use, and epimorphism, it's not so simple. Okay. Another class of examples, lots of examples today, is overcategory. Overcategory. So what is overcategory? If you have a category C and some X in ob C, you can consider the overcategory of X. I think it's denoted like this, but I'm not sure. And it's constructed of all pairs Y and map between Y. So the objects of this will be Y and map between Y and X. Yeah, it's called overcategory because you imagine X and Y over it. And morphism between object here, which is this and this, sorry, is equal to the collection of all, say, here is phi and here is psi, and here is say S between Y to Z, such that the following diagram is commutative. So do you all know what is a commutative diagram?
I don't know.
Okay, I will say. So it's very common in category theory. Each time you have such a diagram, so diagram is just collection of objects and arrows between them. It's called commutative if no matter how you go from one object to another, you get the same answer. So in this case, it says something very simple, that the composition from Y to Z and to X is the same like go directly from Y to X. But sometimes you have more complicated diagrams and they're called commutative if no matter how you go, you get the same answer. Okay. So those are
Rami?
Yes.
So what are the elements, what are the objects in over
X
X?
are pairs of object Y in your category in C, and or triples maybe. No, pairs and morphism from Y to X.
Okay, thanks.
Okay. So this is called the overcategory. We can do some examples here. So for example, if you have the category of sets and you have the object which is just one point, just the singleton. So can you tell me what is the overcategory of a singleton?
Pointed set or something?
The undercategory of a singleton is a pointed set, but we didn't discuss undercategory.
So just set. Just set.
Just set, because any set have a unique map to the singleton, so no additional conditions, so just sets. Yes, we also have the notion of under category. So of course I can repeat the same definition, but I can now make my life simpler. Under category of an object is the over category of this object in the opposite category. No, it's a bad definition because then I have to take opposite. Is the opposite category of the over category of this object in the opposite category. I have to conjugate this notion by taking opposite. Yeah, so under category of point or in sets is just pointed sets. So maps are just maps that maps a point to a point. So one thing that you can notice that if you have a topological space X on top, so you have over of X, and inside it you have this nice category top X. The category whose objects are just open sets and morphisms are just one. There is only one morphism if you have inclusion and no morphisms otherwise. And you see that top X is a subcategory of over X because because special case of a map is just an embedding of a subset to the actual set. Of course, it's much smaller than this one, but still a subcategory. So you remember that we said that the border between two kinds of examples or two sides of category theory is category theory as establishing a language, or category theory as a theory by itself, and examples which are coming from some theory or just some combinatorial or geometric examples. So the border is not really clear. So here you see, so there are many categories here in between. So over category of X is clearly something that came from, like, you have some theory and you want to discuss it, so you have a category that discuss it, and top X is more or less clearly something that have nothing to do with some theory. It's a way to study geometry of a very specific object. And there are many things here in between, which at some point you don't really know at what side to put them.
Rami, when you say topics, you mean what do you mean exactly?
Topics, so I think it was here upstairs somewhere.
The subspaces of the
open subsets here.
Okay.
No, it's not here. Never mind. Just jump to the end. The objects are open subspaces of X, open subsets of X, and this is a poset. And each poset we have a structure of a category.
Rami, can we go again to the over category of a single point?
Mm-hmm. Yes, so what is the question?
So what are the pairs of the over category?
The objects in the over categories are pairs, a set and a map to the singleton. But if you think about it, it's just saying a set because there is a unique map to the singleton.
Okay.
So it's just a category of sets, and any map between two sets will make this diagram commutative because there is no condition here. Yes, X, Y, point, any map. You can do whatever you want and then send everything to a point. You can just send everything to a point at the beginning. Doesn't really matter. Okay, so there are many interesting examples of subcategories of the over category here in topological spaces and in general. So if you have some X, so let's start with topological spaces. So you can talk about fiber bundles. What is a fiber bundle? So you have the over category of X. And inside over category of X, you have a notion of isomorphism of two elements. You remember what does it mean? A map such that you have a map to the opposite direction. And now you have objects of this type, X times F to X projection. So object in over category of X is called fiber bundle if locally it looks like this. So let me say what does it mean. So objects in fib x. Yeah, often when you define category, you just declare what is a set of objects, and you don't really care about morphism because I kind of implied. So now I still will write in the more correct way ob of fib of x, but maybe next time I'll just write fib of fx equal to. So this is equal to all the objects like this in here. I already start lying in the over category over x. So I should have writing ob of over x, but it's too much, sorry. Such that there exists open cover x equal to ui open cover such that let's do it like this. Phi, so phi inverse of ui to ui. This is object of just a moment, x times f. So both of those guys, not x, sorry, ui. Both of those guys, the one here and the one here, are objects in the over category of ui. So this isomorphism is in over ui. Okay.
What is f?
For some, if you want to be exact, you can write here fi for some f in some topological space. So this is called fiber bundle. And if you know what are vector bundles, you can see that vector bundles are somehow fiber bundles with some additional structure, and you can easily say what it is. Yeah, I'm not sure. Okay, maybe I do want to. Yeah, there are some other examples that's going a little bit into algebraic topology, but I probably want to talk about them.
When you mean
Oops, no, next time I want to talk about them.
When you mean isomorphic, do you mean that the isomorphism preserve phi or something?
Exactly, because so those are two objects here, in
projection.
over ui. Yeah, in this category over ui. So this is a category. We define the notion of morphism in that category. You remember where we defined it? We defined what have I done? We find it here, yes? This is a notion of morphism in the over category. So isomorphism in the over category is morphism and morphism to other directions such that the compositions are identity. But each time we're talking about morphisms in the over category, meaning that each time we want some diagram to be commutative. Tal, did I answer your question?
Yes, so although the F is in the top category,
what?
Fi are in the top category,
Fi?
the product downstairs.
Fi are topological spaces.
Yes, are in the topological spaces category. The product is in our category with the projection.
Yes, maybe. Yes, sorry. UI.
Okay.
So this is the example that we. What happens? Yes, this example. Yeah, so this is maybe you can think about it as a point where the category theory start to pace off a bit at least. Yeah, so you probably all heard, or some of you heard, the notion of fiber bundle. And when you give the notion of fiber bundle, you somehow usually specify what do you mean that those two things are isomorphic. And here, since we already defined the category of over X, then we just say that they're isomorphic in that category. Of course, it's not a very convincing example, but it's a beginning. Other questions? Okay. So I think it's a good time to stop because we are out of time, but I just for a moment want to share this other screen. So this is a web site of the old course. The syllabus is the same. So we're still in the middle of the first chapter, or the first topic. The topics are roughly like one topic per lecture, but really roughly. So you can have a look here. I didn't talk about literature. So this is a main book, Sanders MacLean, Categories for Working Mathematician. No, but no, sorry, it's not correct. This is the best known books of category theory, but it's a bit heavy, I think. So I will be more superficial in many places. So there are lots of category theory is something that is very like on the web is very much חרוש. There are lots of sources on the web. Yes, this is something that probably younger people like more. So on this NLab, which is supposed to be now like Wikipedia for mathematics, but it's a very heavy categorical point of view, and in fact even more into higher category, infinity category, etc. So I a little bit give some comments now about what are two categories, and of course after you're doing two categories you can talk about three categories, etc. So this is very modern thing now, and I think even for good reasons it's kind of giving lots of good stuff. But yeah, on the internet it's overrepresented, so probably it's best to read about these things over the internet. Even just category theory, it's overrepresented over the internet, and it's maybe good for us. Questions?
About the homework, where will it be published?
So this is a question to Guy. Guy, you are still here? Guy?
Rami, if you can, then on your site is probably the most convenient.
It will not be a good idea because it will never be on time. So I think the best way is then if you don't have a website of your own.
No, I don't have.
So we can also put a Dropbox folder, or I can share it with you, or you can share it with everyone. Probably best you will share it with everyone, and I will, and you will put there the things.
Okay.
And I can put a link on the calendar and in my website, but websites usually take me time to update it because it's complicated. Sorry.
Okay.
Okay. So, anything else?
Just an suggestion. I think I know the start of category theory, and I think that it would be better if you will be more explicit in. For example, I think that you were not explicit in the definition of isomorphism enough, or what does it mean that the diagram commutes not in the intuition level, but the explicit categorical view, and you always tell I define it, so you can take the dual definition, and you guess that we just can do this in our mind quickly. So I think it will be better if you will be explicit in at first on the.
Okay, so here basically I want to ask you, each time you don't understand something specific, just tell me, and let's try till next time think about any of these stuff that Tal mentioned, any notions that I said that I defined, but maybe I didn't define properly. And at the beginning, please ask me all those questions, and yeah, feel free to interrupt me and ask me questions, and then I will try to be more explicit. Okay, so I'm stopping the recording.